everyone. Today we are talking about UV visible spectrophotometry. Okay, go to the first topic is method development. Method development involves selecting the wavelengths or wavelengths that yield the best result for a particular analysis on a particular instrument. We should define the parameters prior to analysis for optimization of methods such as linearity, accuracy, precision, sensitivity, length, and selectivity. Here, instrument is developed more than in the past. Limitation have less because it's limited modern instruments. Okay, let's begin with linearities.
Okay, first parameter is linearity. Linearity is the ability of the method to produce test results that are proportional to the concentration of analytes in sample within a given range. Beer's law, as you know that the absorbance of a solution are directly proportional to its concentration. If the concentration is greater, the absorbance will also increase as shown on linearity. In figure 1 show the potential errors resulting from inadequate calibration, which x-axis is concentration, y-axis is absorbance. In this graph, show theoretical calibration curve, but in this graph, show the errors that can occur from practice. When measured at the same absorbance, in each color curve give a distinct concentration, which show that the errors that occur from practice can be both greater than 2 values and less than 2 values. And deviation factors are instrumental parameters and sample parameters. In figure 2 show calibration data sets. Ideally, all measured standard values would lie on a straight line, but in practice, the values always exhibit some scatter. So, must apply statistical method to find the best fit of calibration curve to the data, which is linear regression. And next, we are moving to correlation coefficient.
Okay, let's move on to how to select the wavelength for best linearity. When you want to find a wavelength that gives best linearity, you should follow by the correlation coefficients. The correlation coefficient was used to estimate for the standard graph the range of value -1 to +1. If the value is close to +1, that means the best correlation coefficients. In figure 3, there is two graphs which show upper graph y-axis is absorbance and x-axis is wavelength, and lower graph y-axis is correlation coefficients and x-axis is wavelength. Although the graph shows that 450 nanometer is the wavelength of maximum absorbance, but it is identical to the wavelength of 402 nanometer that gives best linearity. When you want to consider with the correlation coefficients, the wavelength of 402 nanometer is the maximum of correlation coefficient, so the best linearity is the wavelength of 402 nanometer. Next parameter is accuracy.
Okay, this parameter is accuracy.
accuracy refers to the closest of measure value to standard or to value. For example, when we shoot the arrow is closest to the target, and when we repeat again, the arrow also in the target. From figure 4, selecting the wavelength for best accuracy. X-axis is wavelength, y-axis is concentration and absorbance. In this graph, we can see the two graphs are related. The maximum, the first graph is absorbance value, which the maximum value of absorbance is the best value. But when we compare the measure concentration is not closest to the two value. So we need to shoot the maximum value of concentration and measure concentration closest to the two value. Which the length around 400 nanometer. Therefore, we need to shoot this point because it's the best accuracy. Let's moving to precision.
Precision is the value of the spectrophotometer specification about the test result with repeated process that being used with the sample from the graph showing example of measurement results and standard deviation, and can be obtained by 10 samples of the same concentration. The standard deviation obtained is precision. The statistic used to determine precision as standard deviation are percent relative standard. Can be obtained by dividing standard deviation by the mean and multiplied by 100. Standard deviation equal 0.0722 and percent relative standard equal 0.07. Standard deviation is low because the graph is small, causing the value is percent relative standard. And from the graph, this good precision. We are moving to the next topic, sensitivity.
Okay, sensitivity has two radical factors to analyze, and the limit of quantification and the limit of detection. In this curve is limit of detection. The limit of detection is the lowest concentration of analyte that can be detected, which used to show the difference between analyte and a substance, and that has signal to noise ratio 2 to 3 fold. And in this curve is limit of quantification. The limit of quantification is the lowest concentration that can be determined with acceptable precision and accuracy. That has signal to noise ratio 10 to 24. And next, how to select the best sensitivity.
And how to find the wavelength with the best sensitivity. It is often estimated that the wavelength with the maximum absorbance and the wavelength with the lowest percent RST or percent relative standard deviation likely will yield the best sensitivity. However, because instrumental noise can vary the wave range and affect to value of mean and standard deviation, and both of these it brings to calculate the percent RSD and will give higher or lower than the two results. And next, this figure is a figure of the technique for yellow dye. The upper graph is the graph of absorbance and the wave range, and the lower graph is the graph of percent RSD and wave range. At 200 nanometer, you can see the same point of maximum absorbance and the lowest percent RSD. So this point is the best sensitivity and optimum range to use. And next topic is range.
Okay, range. Range is interval between the upper and lower level of analyze. It is determined by first analyzing sample that contain varying concentrations. Okay, for example, in this graph show correlation between response and amount. On the left line, indicate difference between maximum and minimum. That is range. But the maximum and minimum is measurable and accurate value. Okay, the last topic is selectivity.
Okay, this is selectivity. Selectivity is the quality of the result that can be achieved without interference or as less interference as possible. Okay, so how to find the wavelength with the best selectivity? In this case, if the concentrations of the analyte is known, the wavelength that gives the closest to the true concentrations. For example, in this picture, we will pick up around the wavelength around 400 nanometers because the measured concentration, which is blue line, get closest to the true concentration. And if the concentrations of the analyte is unknown, the wavelength that gives the lowest concentration likely yield the best wavelength for analyzing because the interference in the matrix sample may gain more content in the sample and can be affect to concentration. So next, how to select the wavelength with the best selectivity. In this figure, on the upper graph, y-axis is absorbance and x-axis is wavelength, and lower graph, y-axis is concentration and x-axis is wavelength. And you can see the sample has been contaminated. The plot concentration and wavelength shows that about the wavelength between 390 nanometers until 420 nanometers likely yield the best selectivity due to have a maximum value of absorbance, which is green lined, and the interference or absorb a small amount, which is red line. And the most importantly than that, the measured concentration get closest to the true concentration. So we move on to conclusion.
Well, to summarize, all parameters that I mentioned before, such as linearity, accuracy, precision, sensitivity, range, and selectivity, we should consider all parameters together. We can use this parameter to determine the appropriate wavelength range in experiment or analysis. Finally, for the experiment results, let's bring two presentation to the end. We would like to acknowledge Assistant Professor Atul Chaibunryang for expert advice, valuable suggestions, and encouragement throughout this project. Thank you for attention.